Oh, the restriction is it's on a sphere. Let's make sure I get the right numbers for 9. Looks like it's 4. Okay, right, now I'm going to do the other thing where I try and make it go into the screen so you can see it. Actually, are you seeing all what I was writing while I was doing it? Are we now looking at a white piece of paper with writing on it?
No, we are.
Oh, good. Okay. So here are the two examples of Lagrange. You've got some function, in this case just x times y, and you're trying to maximize and minimize it under the constraints that 4x squared plus y squared is 8. And then question 9 is a three-dimensional version of the same thing, where you've got a function called x, y squared, z, and it's restricted on this. So I want you to imagine that you took all the points on a sphere with this equation. So what would that look like? Imagine a sphere radius 2, and you're looking at only the surface. And only those points, you were trying to find what's the maximum value of x, y squared, z, and what's the minimum value of x, y squared, z. And then in this one up here, you're trying to take a function x, y, and that's an ellipse. So you imagine all the points on the circumference of an ellipse. So this here is just points on an ellipse. This here are points on a sphere. So Lagrange doesn't care, but that's essentially the geometry of what we're doing. So we'll start off with the first one, question 5. Can anyone remember how to start this fella off? There's a relationship that we write down with lambda in it. If I call this G and I call this F, maybe I made it harder than it seems. Do you remember that guy? Yeah, I know it's 8 weeks ago, but okay. So in this case, I guess I'll take a little note of it.
This is a good thing I decided to bring this one up.
Right, we got this fella, and then we've got a constraint, which is basically this fella. And so delta F is derivative of this guy, so what do we get? We get differentiate partial derivative with respect to x, partial derivative with respect to y. It's going to be lambda partial derivative of g with respect to x, partial derivative of g with respect to y. If you differentiate this function here with respect to x, you get y. If you differentiate this function here with respect to y, you get x. A little symmetry thing going on there. And it's going to be lambda. Differentiate this fella here. If you imagine g of x being basically that guy. Differentiate this with respect to x, you get 2x, and differentiate, no you don't, 8x. And differentiate this guy, you get 2y. What that does is it'll set up a system of relationships. When you equate the x components, y is equal to 8 lambda x, and you can do the second component, x is equal to 2 lambda y. And I'll call this equation 1 and I'll call this equation 2. Now, what we're trying to do here is essentially eliminate the lambda so that we can then find a relationship between the x's and y's, and that relationship will tell us the places where the max and min will happen. Now, there is a step that we need to take, and that is we have to test what happens if lambda was equal to 0. Most of the time, that ends up being a solution that's not usable. But the first time that you forget to do that check is one of those 1 in 10 situations where it actually does give a solution that works, and you should have used it. So it's like Murphy's Law, right? If you do it 10 times, but the 11th time you decide not to bother, the 11th time is the one time that you should have done it. Well, if lambda is 0, then y equals 8 times 0 times x, that makes y 0. And if lambda is 0, you get x equals 0. So that corresponds to a point 0, 0. Now, on our constraint here, You can only use points that have the relationship that 4x squared plus y squared equals 8. Would you agree that 0 is not one of those points? Right, the origin. So we can't use it. Now we return back to our relationship. I'm just going to rewrite it up here again. So we have 8 lambda x and x is 2 lambda y. It's not uncommon for you to use a little algebra trick. And basically, don't you take equation 1 and divide it by equation 2, and the effect is to get rid of the lambda. Remember, that's kind of what we're trying to do, get rid of the lambda. I know the textbook does it another way, but this is the way I like to do it. So if you take equation 1 and divide it by equation 2, y over x will be this guy over this guy. Agreed? Now what happens here is you get y over x, the lambdas cancel, and you get 4x over y. Are you happy about what I just did there? Now, I'm going to rearrange this by cross multiplication. And I now have that relationship. And that's what I'm after. I'm after some type of relationship where I can write y in terms of x or x in terms of y. I don't care how it happens. In this case, y squared is going to be the same thing as 4x squared. You then return to your g of xy formula. You know this guy that looks like this? Which in our case is what? The 4x squared, that guy, equals 8, right? Your constraint. But now I know that y squared can be replaced by 4x squared. So what I get is 4x squared. Instead of a y squared, replace it by the x's, and now I get that. If I combine these together, I get that. If I divide by 8, I get that. And tell me some solutions here. It's not a trick question. Give me an x that works.
1 works.
Anything else?
-1.
Great. -1 plus 1. Now, when x is equal to 1, if you feed that back into the loop, won't then 4 lots of 1 squared, or -1 squared, plus y squared equals 8, won't y squared, why am I doing this? Why don't I just use this information which does it quicker? When x equals 1, y squared is 4 times x squared, y squared is 4 times 1 squared, y squared is 4. Does it not make y plus or minus 2? And if I did x equals -1, would you agree that I don't need to do the working? I can assume that when x is -1, I get plus or minus 2. Put all of that together and you are now left with 4 places to go looking. They're the only 4 places that are of interest, right? They're like the critical numbers from Calc 1. If you're going to get a max or a min, it's going to happen here, right?
Shouldn't that -1 of the y be a -2?
And you're right. Thank you for catching that. Yes. So how do I find out which one is which? Well, don't you find the value of the function, which in this case is xy? Right, at this point, the answer you'll get is 2. When you use this coordinate, you get -2. When you use this one, you get -2. And when you use this one, you get 2. So I have discovered that the maximum value for the function xy is 2, and it will occur at these 2 places. And the minimum value of this function is going to be -2, and it's going to occur at these 2 places. And that's pretty much that question done. I kind of rushed through that a little bit, hopefully not too much. But do you get the flow of how Lagrange works?
I think I get it. So so first you do the derivatives, then you divide it out to get rid of the lambda, and then you just do some quick work.
You do some algebra work to try and solve for x or try and solve for y. Okay. Now, I'm looking at the 3D one, and it's not that I couldn't do the 3D one, and I certainly will if you want me to, but we're kind of, you know, I'm clock watching here. Do you want me, as a class, do you want me to do the a 3D one as well? An XYZ one?
Having
Okay,
seen the,
I got some nods, so we're doing it. I just didn't want to use up your time if you were desperate for something else and we were running out of time because of that. So all I'm going to do for the next few seconds is just rewrite question 9. This is our function. And our constraint you can just think of that guy as being G. You can say -4, which technically it is, but the -4 is not going to do anything because you differentiate it's going to get 0 because of that. So our relationship starts with the gradient of f will be lambda times the gradient of G. And if I do the gradient of f, I'm talking about the partial derivative of f with respect to the 3 variables, followed by lambda, the partial derivative of G with respect to the 3 variables. Okay, keep track of me as I zoom through this. Differentiate this with respect to x, you get y squared z. Differentiate this with respect to y, you get 2xyz. Differentiate this with respect to z, and you get xy squared, followed by lambda. Differentiate this, you get 2x, then 2y, and then finally 2z. I was a little bit fast there, but you're with me, because it isn't that difficult a differentiation.
following.
We cool? Delta f, right? The gradient of f, lambda, gradient of g. Now, when you match them up, the first will do the x's. So y squared z is going to be 2 lambda x, I'll call that equation 1. 2xyz is going to be 2 lambda y, I'll call that equation 2. And xy squared is equal to 2 lambda z, and I'm going to call that equation 3. So far, so good?
Yep.
Right. Now, I'm going to do my, suppose lambda was 0. Can you trust me that you get 0, 0, 0, and it doesn't work? So we'll pretend I did that, right?
Mm-hmm.
Right, we pretend. Oh, by the way, do you know why you have another, and it's a mathematical reason why you have to test lambda equals 0 separately? Do you know that when I do this process, don't I take equation 1 and equation 2 and divide them? Can you see that if lambda was equal to 0, wouldn't this be a very dangerous thing to do?
Yeah.
But since I've tested lambda equals 0, technically what I then say is lambda is not 0. Now let's divide everybody. And that just keeps it kosher, right? Keeps it legal, mathematically. We have got some interesting equations. We have 3 equations to deal with, which makes life typically a little bit difficult, but hopefully doable. So I am looking at these equations, and I am going to take equation 1 and divide it by equation 2. And in equation 1, you get this guy divided by this guy. And on this side, you get this fella divided by this fella. So let's do this and see what we get. Won't the 2's cancel and the lambdas cancel, so you get x over y? Great. 2 cancels, lambda cancels, x over y. Over here, won't the z's cancel? One of the y's cancel, and it looks like I'm going to have y over 2x. Are we comfortable with what I just did there? Okay, where are we off to now? What's the next line of algebra going to look like?
Y squared equals 2x squared.
And I'm just going to leave that there. If this was a 2-dimensional question, wouldn't I now be plugging that into the g function and get plus and minus 1s and plus and minus 2s like we did before? But right now I have to leave that one because we don't have just x's and y's. We have x's, y's, and z's, and I have to figure out how to figure out that. Right now, I know that y's can be replaced by x's or vice versa, right? So I've got those 2 paired together, locked in a relationship. Now I'm going to go back And I'm not allowed to do 1 divided by 2 because I would just get back to here. I'm going to look at something else divided by something else. So give me 2 equations to divide, and let's see where they lead.
2 over 3?
Which ones you want?
2 over 3.
2 over 3. Now, if you take equation 2, which is this guy, and you divide it by equation 3, which is this guy, and if you take equation 2, which is this guy, and you divide it by the other one, you get this guy. Let's see, 2's cancel, lambdas cancel. That's a good start. An x cancels, a y and a thing cancels. It looks like I'm going to have 2z over y. If I make a mistake, tell me. Does that look good? Looks good to me, but I have been known to make mistakes, right? I know it's hard to believe, but it is true. Okay, now if you do the old you go here and I go there thing, cross over, don't I now have y squared is equal to 2z squared?
You sure do.
Right. Are we good? Right. Now, I have already y squared equals 2x squared. I'm about to do this. We have x squared plus y squared plus z squared equals 4. Right. Now, if I rearrange this fella here, isn't that the same as saying x squared is a half y squared? So this fella becomes a half y squared. Doesn't y squared stay as y squared? And if I rearrange this fella, can't I say that z squared is a half y squared? Do you see what I've managed to do is to take the equation and reduce it down to a 1 variable question? You can't solve equations with 2 variables, and well, you can't do it if there's only 1 equation. And we've only got 1 equation, right? We've only got g. So when you do it this way, do you see that we now have 2y squared is 4, so that makes y squared 2. Go with that? Half and a half gets you 1, 2. Divide both by 2. Got that? Won't y be plus or minus the square root of 2? Now, if I use that relationship over here where my finger is pointing, y squared becomes 2. I know, I might write it down. Right, that's this guy. If you plug in plus or minus 2, it won't matter. When you square it, you still get 2. Do you see that you get x squared as 1, which means x is now going to be plus or minus 1? So x's can be plus or minus 1. Y's can be plus or minus 2. All I really need to do now is figure out who z is.
Z is the same as x.
And z has the same relationship as x's. Agreed? So that makes z is going to be plus or minus 1. Now, when you put this package together and you put it in order, it does get kind of messy. If you want to compact it, the relationship is that. Do you recognize that as actually 8 distinct points? Right? There's 8 of them, right? 2 times 2 times 2. Just one random version of that could be that guy, right? But there are 8 of them, so I'm not doing this bit. But see, for every single one of them, those 8, wouldn't you then return to x, y squared, z? Plug in the x, plug in the y, plug in the z, and you get the answer. And the biggest answer is your max, and the smallest answer is your min. And you're probably going to find that half of them end up being the max, and the other half end up being the min. But there's no reason why all the points you find end up being part of your solution. But at least you have to test them to see if they are. Are we good? Right. Now, you can imagine, because of the workload involved in a Lagrange multiplier question, that you're not going to get 3 of them in the final, right? You'll get 1. But that's true for everything. If you get it, and I have to say if, because you won't get everything, but if you get Stokes' theorem, they're going to be 1. And if you get the divergence theorem, they're just going to be 1. Do you see that all the major signposts of the things that we've done are typically going to be 1? Do not expect too many questions from the early stuff. I don't need to ask you to find the partial derivative of a function, because aren't you going to have to find the partial derivative of a function in all the other stuff that comes later anyway? Right? I don't even need to really, although I might, ask you to do a double integral or a triple integral just on its own, because don't double and triple integrals, or at least in some of the stuff that comes later, you end up having to do anyway, right? So you will get to do these things, but you may not get to do them. I guess what I'm saying is you may not get to do them as an individual question, but you will get to do them as part of a bigger thing. So Lagrange is a good example. Partial derivatives being used, for instance. Okay, that works pretty well. It's not too long. What you got? Any question? Any topic?
Nobody's gonna speak up. Go over some Stokes, since I also missed that one.
Whoa, Stokes, he is a good one. Let's find something for you. I'm not trying to do a Stokes on its own, because it's like Lagrange. You better pick a book one or it won't come out well. That's basically the bottom line. So if you can hold with me. Let's see. We're on current, aren't we? Oh, I got a better idea. Why didn't I think of this before? Right, so the question is, how do you do Stokes theorem? In a few seconds from now, hopefully. Here we go. Gives me a chance to sell something. If you go, oh darn it, I'm hitting so many buttons, I don't know where am I? I've lost you. Oh, here you are. Let's share the screen I want to share. It should be this one. Right, are you all looking at 264, chapter 15, 16, all that good stuff? That's exciting. Right, hopefully you've noticed that this is where all your stuff is hiding. And here's videos on Stokes theorem, so there's some videos for you to watch. What I think some of you might not have noticed is that at the bottom there's PowerPoints, and then later on there's some homework examples. So for instance, if Rachel has a real hassle with that spherical one, then I would probably put it there, right, when it's finished. So if I click on, there we go. If you click on this thing, you'll find, depends on what the heck's going on, but you'll find different PDFs of different things, and here we go with Stokes theorem. So since I only have a few minutes and I figured out I won't have time to do one from scratch, what I suggest you do is you go and you look at this guy here, right? So boom.
Oh, okay.
Right, but we'll talk through. This is essentially what Stokes theorem allows us to do. It allows us to get a line integral, and it turns it into this fella here. That's one of its versions. But it's more likely that you're going to get this version here, where you're trying to find a double integral, a surface double integral, and you convert it into, in this case, a line integral. So here is very quick version. I'll do the second one, a better example. Here's a very quick version of how the process works. Suppose you want to evaluate this fella, right? this particular line integral, you turn it into this fella here then. So here is your f, and C is a triangle with a number of points. So f is this guy. The curl of f is this fella. Right? Remember to do the curl? You end up with that guy there. Then what you do is that you are essentially going to take this line integral and turn it into this surface integral here. And the guy that's curl f, I've decided in the notes just to call it g. And so what you then can do is you can find this surface integral by turning it into a good old-fashioned double integral. Double integrals we're comfortable with, surface integrals not so much. And the formula for it is negative p this guy, negative q that guy, plus r dA. And it's just a piece of magic that you're told. So if g is this guy, p is negative 2z, q is negative 2x, and r is negative 2y. And how do you get d? You imagine the surface being projected onto the floor to give you the two-dimensional area on the floor, which we call d. So if you took, in this case, this triangle, and you imagine this triangle being projected onto the floor, you would end up with a little triangle that looks something like this. I didn't draw the picture, but if you imagine it, it'd be a little right-angled triangle with a diagonal line going down the way. So that's the region D. So that's where these limits came from. You then basically plug and chug. Now, sometimes you don't need this step here. When you're doing the double integral, you get to a line, something like this one here, and then you're about to start integrating. Unfortunately, sometimes there's a z left over. If there isn't a z left over, you're done, right? Just keep going. But if there is a z left over, you have to change it into x's and y's. And so you might say, well, what function is z? Z is the equation of the plane. In this case, that guy there. So imagine these 3 points being joined in 3D space. If you find the equation of that plane, and you're just going to have to trust me, because I skipped some lines, it's that fella there. Or if you rearrange it, x plus y plus z equals 9. And that's why that z there turned into that fella there. And then you do tidying up and then integrate your way to the end. And that was us. We got perfect time.